Alright, now that we have the idea of sets defined, we can talk about using Venn diagrams, which are a graphical modeling tool, for us to be able to represent these sets. First thing we'll want to talk about is a universal set U, and that contains all of the objects under consideration. That'll change depending on the problem. So if we do an example, we'll say draw a Venn diagram for U, the set, not U, for V, the set of vowels, in the English alphabet. Then here, the set U would be all letters of the English alphabet. Let's go ahead and draw a box here, and we'll label set U up in the top right corner. It's a standard place to label your universal set. And we'll say universal set is all English letters. And then we'll draw a circle, and this is going to be set V for the vowels, and then we'll draw points for each one of the vowels. So point there, we'll label it A, maybe we'll put U over here, E can go over there, O can go here, I can go there. And then if you were going to fill out the universal set with all your English letters, those letters would be out here, and those would be your consonants. That's not a capital Z. Okay. Alright, so now that we have an idea of what the Venn diagrams look like, let's go ahead and move on. And we'll define what subsets are. So, do another definition. Okay. We'll say the set A is a subset of set B if and only if every element of set A is also an element of set B. We use the notation A is a subset of B. Notice that looks very similar to less than or equal to, but it's not a point on this. This is rounded. So it's a subset, and then the straight line under it technically meaning subset or potentially equal to set B. To include oops, sorry, not to include, to indicate that A is a subset of B. And then if we want to draw this out as a quantification, we can write this as for all x, x is in A, then x is also in B. Okay, so that would be the quantification of this subset. So for all x, if x is in A, then x is in B. We'll do a note. We'll say to show A is not a subset of B, we need only to find one element where x is in A and x is not in B. And this would be a counterexample. All right, let's do an example now. We'll say the set of all odd positive integers less than 10 is a subset of the set of all positive integers less than 10. And that one obviously makes sense. If you've got all positive integers less than 10, and then you list out all the odd positive integers less than 10, clearly all of the odd positive integers will also be in the positive integer set. So that one will hold true. Similarly, you could say the set of rational numbers is a subset of real numbers. And you could take this to all kinds of different examples. We could say something like the set of all CIS majors and VVC is a subset of all students at VVC. And if we're going to draw this kind of a relationship in a Venn diagram, draw out our square, U being our universal set. Whatever set this is, we'll call it B. And if A is a subset, then it's completely contained within the circle of B. So it would be like that. And that would be a visual representation for your subset. Okay, now that we know what subsets are, we can come up with a new theorem. For every non-empty set S is guaranteed to have at least two subsets, the empty set and the set itself. So you would write this like, for every set S, you've got the empty set is a subset of S, and you've also got S is a subset of S. And remember, since it's the subset is subset or equal to, that's why the set itself is listed under this definition to be a subset of itself. Okay? And then let's go ahead and do a proof of this. We'll say let S be a set. We'll say to show that the empty set is a subset of S, we must show that for all X, if X is in the empty set, then X must be in set S. We must show that that is true. And then we can say, all right, well, since the empty set contains no items, are elements then X being in the empty set is false. Therefore, the conditional is true. And therefore, the empty set is a subset of S. Okay. Then we have definition of a proper subset. And we'll say when we wish to say that A is a subset of B, but A is not equal to B, we write A being a proper subset of B, and say A is a proper subset of B. And then we can say for A being a proper subset of B to be true, it must be the case that A is a subset of B. Notice that's the subset or equal to, and there must exist an element X in B that is not an element of set A. That is, A is a proper subset of B if and only if for all X is an element of A, then X is an element of B, and there exists an element X where X is in B and X is not in A. So essentially this is just what we wrote out in that whole paragraph above. You start with the existing definition of a subset, meaning for all X, if X is in A, then X is in B, and your new thing that we added here to be a proper subset, being there exists an element X where X is in set B and X is not in set A. And that's how you show that it's a proper subset. Okay, now that we have the definition of a subset as well as a proper subset, that leads us to the next thing, which is how do we show that two sets are exactly equal? You can show that each is a subset of the other. If you can show that two subsets are equal, are each subsets of each other, then they are by definition going to be equal. So that means that A is a subset of B and B is a subset of A, then A is equal to B. Okay, another way to write that is A is equal to B if and only if for all X, X is in A, then X is in B, and for all X, X is in B, then X is in A. Put those two together and you get for all X, if X is in A, then X is in B, and if X is in B, then X is in A. And that's why we have the if and only if operator there. And that finishes up this section.